Hello, Math Tutu Free students. In this video and activities, we want to practice linear combinations. Let me quickly review what was the definition and then we go over the exercises. If we have vectors, let's say v1, v2, all up to vn in, let's say we have n of them and it's in Rm. These are columns in Rn, or they are column matrices with size m. So a linear combination of these vectors, it's a scalar multiple of each and added by each other. So it's an expression like this. C1, V1, C2, V2, sum of these all the way up to Cn, Vn, where the coefficients are scalars, or in this course, scalars are real numbers, so they are some real numbers. Such thing, it's called a linear combination of this. And we have another terminology that a new vector, let's say vector v, which is again in Rm. In what case we can say that this can be written as a linear combination of these vectors, or it cannot be written. Or we say that this is a linear combination of these vectors, or it's not. What is the meaning of this? It exactly means that there is a linear combination of these, which is the same as this vector. In other words, there are some scalars C1 up to Cn such that V is the same as C1 V1 plus C2 V2 up to Cn Vn. That is exactly the meaning that this can be written as a linear combination of this. There are C1 up to Cn, that this is true. What is the meaning of this thing that we are saying? If you look at this, and if we do it in one of the exercises, if you write down these in columns and write down the properties that this should satisfy, you see that this is actually a linear system of equations. And by saying that there are some C1 up to Cn that this is satisfied, basically you are saying that this linear system of equation in unknowns C1 up to Cn has at least one solution. In other words, it's consistent. So we are saying that this it can be written as a linear combination of those if the linear system that is expressed by this equation is consistent in unknowns this, or has at least one solution. If it is inconsistent, so there is no C1, C2 up to Cn that this can happen, then this is not cannot be written as a linear combination of V1 up to Vn. Note that like any other system of equation, it could be inconsistent, or even if it's consistent, it can be unique solution or infinitely many solution. Maybe there is a unique way that you can write V as a linear combination of V1 up to Vn, or it is possible, but there are infinitely many possibility that's how you write V as a linear combination of other vectors. That depends on if the linear system has infinitely many solutions or a unique solution. Now let's do these exercises. Exercise 1, we want to see which columns can be written as linear combination of these two vectors. Let's look at a general linear combination of these two vectors and see how does it look like. 1, 1, 2, 2. Okay, so a general linear combination, it's like C1 x1 plus C2 x2, where C1 and C2 are two real numbers. Let me use the what is x1? It's 1, 1. X2 was 2, 2. And let me compute this. That is C1 plus 2C2. And the same, C1 plus 2C2. where C1 and C2 are two arbitrary real numbers. So a completely general, all linear combinations of x1 and x2 are in this form. They are columns, looks like this. But look at this column. The first coordinate and second coordinate are the same. And this value, it's coming from a combination of two arbitrary constants. So two arbitrary real numbers. So why not? Why C1 and C2 are arbitrary real numbers and are changing? Why not give a new name to this as a new arbitrary real number? And then this, it's the same as that. So if I do change the name of these two scalars, this combination of these two scalars, C1 plus 2C2, and take it to be C, then this vector is nothing other than C. But now, when C1 and C2 are arbitrary real numbers, C1 plus 2C2 will be a new arbitrary real number. So C, it's arbitrary real number. So in other words, I showed that all linear combinations of x1 and x2 are in this form, are column vectors with the first coordinate and the second coordinates the same. So that's the answer for the first question. It's all column vectors that the first coordinates and second coordinates are the same for any C in R arbitrary. These are all column vectors that are linear combination of this. Now for the second one, we should do basically the same thing. So C1 E1 plus C2 E2. This time my vectors are these, my columns are these. So if I put 1 0 and 0 1 as the second one, what do I get is C1 0 plus 0 C2, and this is C1 plus C2, not plus, C2 as second coordinate, C1 C2, where C1 and C2 are two arbitrary real numbers or two arbitrary scalars. Now look at what did I get. These are all linear combination of these vectors, and what I got is uh, all columns which have arbitrary first coordinate and second coordinate. So basically they are arbitrary, that means it's basically any column of size 2. So any column of size 2, basically what I showed is that any column of size 2, it's a linear combination of E1 and E2. So we can say that any column V in R2, it can be written as a linear combination of this. Or if you like the other version better, it's basically any column with any arbitrary first coordinate and second coordinate. We will discuss this thing later on, in the sense that, oh, this is actually a basis for R2, in the sense that everything can be constructed by linear combination of these two. These are good building blocks to build the whole R2. We will discuss this concept of spans, linear independence, basis in much more details. In details, you don't need to know it now. Later on in the course. As the last part, let's do this exercise, which I want to see, can this be written as linear combination of these two or not? So let me write down this meaning of this expression, that this can be written as a linear combination of this. So we are saying that I want V to be a linear combination of x1 and x2, C1, x1 plus C2, x2. But what is, let me bring this a little bit down so I can see the equation of the expression for x1 and x2, okay? But V, it's this. Let me write it down. 3, 1, 2. I need to get a system of equation out of this equation to solve it. Then C1, x1. x1 is this. 1, 2, 1. C2, x2. x2 is that. 1, -3, 0. Let me simplify the right-hand side. That's C1 plus C2. It's 2C1 minus 3C2. And finally, C1 plus 0. So basically, it's a linear combination of those two vectors, or it's a dislinear combination of those two vectors if and only if this column is the same as this column. Two matrices are equal, or in particular, two columns are equal if the entries are the same one by one. So they are the same entry wise. So this is the same as this is the same as this, and this is the same as this. And that is the system of equation that I was talking about. So from this, I get a system of equation. Let me write that system of equation on the next line. So that is C1 plus C2 should be 3. 2C1 minus 3C2 should be 1. And C1 should be 2. For a general, we have seen in the first week that how do you solve a general linear system of equation using augmented matrix and row operations. So no worries, I can do any system of equation. But this one, it's very simple, and maybe it's faster to not use augmented matrix because I already have C1 and I only need to find C2. If I use this in the first equation, I find C2. C1, which is 2 plus C2, will be 3. And this gives C2 equals 1. Now I haven't used this equation. I need to check that actually these that I found is consistent with the other solution. Let me check that. If C1 it's 2 and C2 it's 1, then you have 2 times 2 minus 3 times 1. It's 4 minus 3, which is 1. So this equation is also satisfied. That means this is a solution for the system. And actually, it is a unique solution because any solution should satisfy this and also should satisfy this. Hence, it should satisfy this. So this system has a unique solution, and that unique solution is this. What is the meaning of this? Having unique solution, this. That means, first of all, this vector can be written as linear combination of this, and only there is a unique way to do it. What is that unique way? It's V equals C1, which was 2, x1 plus C2, which we found as 1. 1x2, which is just x2. So basically, we proved that this V, it's 2x1 plus x2, hence it can be written as a linear combination of this. And this is the only unique way that we can do that. So actually, that's the only linear combination of x1 and x2, which equals to V. Let's double check that actually this it's correct. Let's compute 2x1, 2 times that. It's 2, 4, 2. And add x2 to it. What do we get? 2 plus 1, 3. 4 minus 3, 1. 2 plus 0, which is 2. That's the same as this column. Yeah, actually we solved the system of equation correctly. We didn't do any computational mistake. As an exercise, I want to redo it. Try to do this. That can this be written as a linear combination of these? I won't redo it, but I explained or mentioned the final answer to you. So basically, everything is the same, except here it changed to 2. So that's the same. You get 2 from these two. You get a still C2 equals 1. But when you put C1 and C2 that you found in this equation, you see that it is not 2. That means actually this equation with the other two equation is inconsistent. So we don't have any solution. There is no solution to this system of equation. And that means this cannot be written as linear combination of this. And you can make an example, not necessarily on this example, but maybe on other examples that you can do it, but in infinitely many different ways. You cannot make such example from these. We will see again later what is spans, linear independent, basis. Basically, these are linear independent, and because of that, we will see later in the course. There is no way either you cannot do something with this building blocks, or if you can do it, you can do it in a unique way. So, but you can consider other building blocks that there is not unique way to write them as linear combination. Let me give you a very simple example. Let's consider three vectors 1, 0, like this example e1, e2, 1, 0, 0, 1, but also 1, 1. Then any vector can be written as a linear combination of this, but there is not unique way to write it. For example, 1, 1, let me give a name E1, E2, and E3 to this, let's say. Or let's say V1, V2, V3. Then consider this vector. This vector can be written in at least two different ways as a linear combination of this. It can be written as 1v1 plus 1v2. If you add these two vectors, you get that. Also, it can be written as 1v3. So these are two different linear combination of these three vectors, which gives the same vector. So there is not unique way to do it. So since we have seen that it comes from a linear system of equation, when there is at least two ways to do this, then there are infinitely many ways to do this, because a linear system of equation either has no solution, unique solution, or infinitely many solution. So actually there are infinitely many ways that you can write this as linear combination of these three vectors. We will call this case as we assign a name that these vectors are actually not independent from each other. They are linear dependent. That's why we have redundancy in their linear combinations. Again, moreover towards later in the course, we will study very important concept, which is linear independence, spans, and basis. This is just a glimpse of it, a start of it. We will study these later. Okay, that's all for now. Thank you for watching.